I think I will get started. I think in today's class, I want to spend some more time, a little bit more time talking about this regression with the regressors. Okay, the time series with regressors. So today I want to spend a little bit of time talking about the forecasting, and then we will move on to a very interesting new topic, the Gauge model. Okay, so I think to do the forecasting, I want to use this example. So this is, again, also our example that you have seen earlier. This is the SOI. Okay, so the SOI measures the changes in air pressure related to the surface temperature in the Central Pacific Ocean. Okay, so that's the SOI. I think the Southern Oscillation Index. Okay, something like that. Okay, so this is a plot of the SOI. Minimize this. Okay, so this is a plot of the SOI. So for me, I do not see much heteroscedasticity here. So what I do is that I also plot the log of SOI. Yeah, and it looks like taking the log is not a very good idea, a couple of reasons. So first is that the SOI seems to have some negative numbers. So taking the SOI on the negative numbers, taking the logs on the negative numbers does not work. Okay, so we would have some missing values. And here you can also see that it looks like when I took the logs, the data becomes actually more heteroscedasticity. So which is something what I want. So I think just for this SOI data, I don't think I will go with the log transformation. Okay. Okay. So now I want to do some predictions on this SOI. So instead of using those autocorrelated stuff, I want to use the time to predict SOI. Okay. So this is what I did here. So I want to use time to predict SOI. Okay. So to generate the variables for the time, we just use this time SOI. And what we got, and I call this variable trend. Okay. So let me show this trend to you. So let me first show you what is SOI. Okay. So this SOI is this type of data sets. Okay. So it's from 1950. January 1950, okay, all the way to, I think, yeah, all the way to 1987. This is September. Okay, so it's a monthly data from January 1950 to September September 1987. Okay, and let's see what the trend looks like. So trend is the time of this time series. Okay, so this is what the trend looks like. Okay, so for the January 1950, it gives its number 1950. And for the February 1950, it gives its 1950.083. And this 083 is just 1 divided by 12. Okay, because we have 12 months of data, so I think it's just divided by 1 over 12. Okay, so then March 1950 is 1950.167. Okay, and once we to September 1987, it is 1987.667. Okay, yeah, so that's what's the this time command does. So it automatically transform the time to a time that you can run your regression. Okay, so once I have this trend variable, then I just run this simple regression. I run a regression of SOI on trend, and this trend is just the time. Okay, so this is what I got. So I run this regression, and you can see that both the intercept coefficient and the slope coefficient are statistically significant. Okay, and remember, if we want to include a trend in our time series analysis, we need to check if the residues of this like simple regression is white noise. If it is not a white noise, we will try to fit an ARIMA model to it. And if it is white noise, then we are basically done. Okay, so now let me plot the residues and see what it looks like. Okay, so that's the residues. Okay, so looks not bad, right? Just by looking at it, I think it's not that bad. So the mean is looks like it is 0, and it's like homoscedasticity. But just looking at this graph, I think it's relatively hard to tell whether it has some serial correlation. So what we do is that we will plot its ACF and its PACF plot. Okay, so this is the ACF and the PACF plot of the residuals of the regression. Okay, so you can clearly see that the ACF and the PACF plot says that the residuals is not white noise. Okay, so we have a lot of bars both in ACF and in PACF that are outside the confidence interval. Okay, and moreover, we realize that it seems there's some seasonality pattern left in the residual plot, in the residuals. Okay, so in the ACF, you can see the bars in leg number 1. This is like leg number 13, leg number 25. So you can see like this seasonality pattern. And similarly for the PACF, you can see 1, 11, 13, 25. You can see the seasonality pattern. Okay, so they suggest the ACF and PACF plot suggest the residuals are not white noise. Okay, so that means we need to fit a SRAMA model to it. Okay, yeah, so then I try to fit an SRAMA model to these residuals, and I can tell you that I actually spent some time to fit the SRAMA model to it in order to get what I think a satisfied model is. So it's not a very easy task to find the best model or the optimal model. Okay, so let me go over this with you. So I first look at the ACF and the PACF plot. Okay, so I easily notice that the PACF has this very large lag at leg number 1. Okay, and I think like this PACF somewhere like tails off. Okay, but the tails off like follows this seasonality pattern. Okay, and I know that this data is a monthly data. Okay, so the first model I think is this model. So I fit a SRAMA 100 100. Okay, and the seasonal time period I choose is 12. Okay, and the XREG, the X variables I include in this regression is this time variable. Okay, so then I fit this as a remote model. Okay, so you can first easily notice that this LB statistics are not very good, actually are very bad. So all the p-values are less than 0.5, so that means 0.05. So that means our model is not a very good model. And moreover, you can notice that the ACF or the residuals, there are a couple of bars that are very large. And I also noticed there are still some like seasonality patterns left here. Okay. Yeah, I also switched back to the coefficients, and I realized that the coefficients, the XREG, the coefficient of this X regressors is not statistically significant. It's actually statistically insignificant at the 5% level. Okay, so this is actually looks like just by looking at this ACF and PACF plot, it looks like this 100 100 12 model is a good starting point, but it turns out it's actually not a very good model. Okay, so this is not a very good model. A couple of reasons. So the XREG is insignificant. ACF of residuals, not good. LB statistics, not good. Okay. So what I do next is that I try to increase the order of the AR part a little bit. Okay, so I just try to include like this as ARIMA from 100 to 200. Okay, and I run this model. Okay, and it looks to me that there's not much improvement, actually. So I still find like the ACF residues are not very good. The LB statistics are not very good. Okay. So the next thing is that I try to increase the order of this seasonal ARIMA part, this seasonal AR part a little bit. So I increase 1 to 2. Okay. Yeah, and actually you can notice that like this iteration, this estimation really takes some time. And this is what I got. So again, I do not think that there's much improvement here. So the LB statistics are still very bad, and the ACF residues improved a little bit, but still not that good. Okay, and also the XREG, the coefficient is statistically insignificant. Okay, yeah, I think I have a question. Yeah, what XREG is doing. Yeah, so the XREG is, so in this example, the XREG is just the trend, okay? And the trend just measures the time of the SOI. Okay, so let me open the trend for you again. Okay, so the trend is now is a sequence of variables. It's just a sequence where the first observation, 1950 January, it is 1950,000. And 1950 February, it is 1950,083. Okay, and this 083 is that basically it's 1 divided by 12. Okay, because we are having this monthly data. So this trend measures the time of this SOI. Okay. Yeah, and just recall, like in our previous example, in last example I did last class, or let me, so you might focus. So for example, like in some of your analysis, you want to study like the effect of like the COVID on some economic variables, then the XREG there gonna be the COVID, the number of new COVID-19 cases, okay? Okay, so now let me just resume. So what I got is this regression. I still find this is not good. So I think that I might left some, yeah, there might some like, I perhaps do not do some like seasonality difference here, because I realized that this ACF plot has this seasonal patterns, okay? So I try this model then. Okay, so this is a model that I try. Okay, so I try to increase the seasonal difference here. Okay, and again, I realized that the ACF plot seems to look a little bit better, but the LB statistics are still very bad. Okay, and this XREG is still statistically insignificant. Okay. Yeah, so you can see, yeah, and actually, like at that point, I'm a little bit disappointed, because I think just by looking at this ACF and this PACF plot, I think that this ARIMA 100,100,12 model is a good starting point, but it looks like the models like it's actually not very good. So then what I do is that I include some like A part in this model, even though that just by looking at this graph, I do not think that there is that much MA part in it, but things like if I just focus on the AR parts, the model is not good. So I try to include some MA part in this ARIMA model. Yeah, and you can see like the calculation actually takes a lot of time. Right, so again, I find that the LB statistics are all significant, suggesting this is not a good model, okay? But the good thing is that I realize that this AIC and this BIC actually improves a lot if I increase this MA terms. So just remember, just say like the AIC here is 0.245, the BIC is 0.317. However, the AIC in the previous models are just like 0.46 and the BIC is 0.51. Okay, so both of this AIC and the BIC are larger than the AIC and the BIC I consider here. Okay, so I think I at least have some improvements once I include this MA part in the model. Okay, even though like this LB statistics really has a lot of problems, this is, I think, not acceptable. Okay, yeah, and I also tried some other models, and still I find that like LB statistics are still very, very bad. Okay, but the lucky thing is here is that another improvement I got here is that if I decrease the S-arima part from 2 to 1, I realize that now all the coefficients become statistically significant. Okay, but anyway, the LB statistics is not very good. Okay, so I think I want to make something here. So okay, so now all the coefficients are statistically significant. All the residual plots look good, except the LB statistic. Okay. And I also want to write the AIC and the BIC down here. Okay. Yeah, so it looks like there must be something wrong here. Okay, so what I do is that I went back to this ACF and the PACF plot again, okay, and see what part I miss, okay. Then I realized that even though this is a monthly data, but it looks like this seasonality pattern actually happens maybe like in the leg number 6, right? Did you see that? Like after leg number 6, I do have like some bars that are outside this confidence interval. Okay, so this is like 0, this is 6, 12, this is 18, 24. Okay, and similarly for the PACF plot, I also realized that like this seasonality pattern actually does not happen every 12 months. It seems that it happens like every 6 months. Okay, so I see like after 6 months, the PACF, like the bars of the legs, become statistically significant. Okay, so based on this, I think I might want to change like the seasonal part from 12 to 6. Okay, and this is actually what I do. So I first consider this 1001006 model. Okay, and I run this S-arima. Yeah, and now I realized that, yeah, I got at least the LB statistics have something like improved, right? So you can say like at least for the first maybe 7 or first 6 legs, they are statistically insignificant, suggesting that my model is good, okay? But I realized that I still have like this ACF residual plot is not very good. It still have some bars outside of this confidence interval, but I know this maybe can be solved by introducing the seasonality difference in the model. Okay, and I also realize if I change like the seasonal from 12 to 6, I realize that all the p-value of the coefficients become statistically significant, which is again a very big improvement. Okay, yeah, just comparing this model and this model, the difference is that I changed 12 to 6, and I have a bunch of improvement. Okay, so I have the LB statistics improvement. I have like this, the coefficient of significance improvement. Okay, so I think I might now on the right track. So then this is what I did. Okay, so I increased the order of the S-arima, the AR part a little bit, and it looks like the LB statistic becomes worse again. So then I try a couple of models. Yeah, and this, I think when I finally move down to this model, the things now I think becomes acceptable to me, okay? So this is like the SRAMA 4002016 model, and the trend is X variables, okay? So now you can see right now all the coefficients except this AR2 coefficients are all statistically significant, okay? And all the residual plots looks not that bad. Okay, so the ACF of the residuals is not that bad. The LB statistics, at least like from lag 14, we have like all these lags less than 0.5, but all the lags before like lag 14 are larger than 0.05. Okay, yeah, so yeah, so I actually spent quite amount of time like trying to find the best model on this. And this is a model that I think it is acceptable. Yeah, so you can definitely try more models after class. And if you find like better models, you feel, please let me know. I really like spend a lot of time trying to find a good model on this. Yeah, so that's, I think that's probably the things that you might encounter in your final project. So you actually might find like fitting a model is actually not that easy, okay? Yeah, and also, yeah, also I realized that the AIC and the BIC for this model is the lowest. So the AIC here is 0.202 and the BIC here is 0.293. Okay. Okay, so yeah, after spending quite amount of time finding the best model, I think this is a model that I want to use for my forecasting. Okay, so how to do forecast? So to do forecast, if you have X regressors in your model, it's actually different from the model that without an X regressor. The reason is that I discussed earlier, because if you want to do those predictions, then you actually need to know those X variables. You need to know the values of those X variables. Okay, so for example, again, like the example, let me give this example. So for example, if you want to study the effect of COVID-19 on some economic variable Y, okay, then that means you actually need to know the number of COVID-19 cases. Okay, so for example, if you want to, I know some of you want to study like the unemployment rate. So if you want to study the effect of COVID-19 on unemployment rate in, let's say, June 2021. Okay, so that means you actually need to know the number of COVID-19 cases in June 2021 in order to make the prediction. Okay, however, or unfortunately, the COVID-19 cases in June 2021 is actually not observed now. It's not observed in April 2021. So that means you actually cannot make the prediction. Okay, but in some cases, we can actually do the prediction. So here is an example that you can actually do the prediction. The reason is that now we use the trend, I think here, yeah. So now we use the trend or the time of the SOI as a predictor. Okay, so if we want to say predict the SOI in year, say like 2020, June 2020, we know the X variable or the value of the X variable gonna be 2020.5. Okay, so even though we are not at that point, but we know the X values should be that number. Okay, so let's do the prediction here. So let's do a 12 months ahead prediction. Okay, so let's set the n dot ahead equal to 12. Okay, and let's have this variable. Let's call it a new reg. Okay, and this new reg is generated as this. I will explain this later. Okay, so let me open new rec for you. So what is new rec? Okay, so remember the last SOI we have is, let me pull up trend. So the last SOI we have in our data is 1987.667. Okay, so this is September 1987. Okay, so the next prediction we want to do is October 1987, right? October 1987. And what is X value for October 1987? It should be 1987.750. Okay, and let's see, 1987.750. Okay, so this corresponds to 1987 October. And similarly, 1987.833 corresponds to November 1987. And this is December 1987. And this comes to January 1988. Okay, so we want to do the prediction from 1987 October to 1988 September. Okay, and we know the X variables, the values of the X variables from 1987 October to 1988 September is 1987.750 all the way to 1988.667. Okay. Okay, so no question about this. Okay, any questions about this? Okay. Okay, and then let me tell you like what this command does. Okay, so this is the first part of this new rec. This is called time SOI, then brackets length SOI. This would give you the last number of the trend in the SOI. Okay, so this is 1978.667. 1987.667. This is the last observation in our data set. And this corresponds to September 1987. Okay. And the second part of this new rec is a sequence. Okay. And this is a sequence from 1 to number of ahead predictions we want to make. So now it's a sequence of 1 to 12. Okay. But since we are considering a monthly data, so we will divide like all this number by 12. Okay, so if you divide all this number by 12, this is what you got. Okay, 0.0833, 0.167, 0.250, stuff, things like that. Okay, and then you will combine this part, like this time SOI, length SOI part together with this sequence part. Okay, so this basically is combined by this plus sign. Okay, so basically it's that you will add 1967.667 to all these numbers in this sequence. Okay, and once you do that, you will get new rec. Okay, so the first number is 1987.750, which is October 1987. Okay, so which is the first time period we want to do the prediction. Okay. And this is the second number, 1987.833, which corresponds to the time of November 1987. It is the second time period we want to do the prediction. Okay, and this is a third, this is a fourth, this is a fifth, this is a sixth. Since we want to do the 12th prediction, so the last number we have is 1988.667, which corresponds to September of 1988. Okay. All right. So now this is a code that we will use to do the forecasting. So the difference from previous forecasting is that so these are the same. So these are the time series we will use to predict. This is SOI, and the number of ahead prediction is 12, and the model we consider here is 4002016, so which is this model. And the X-rec we have is the trend. The difference is this part. So in this part, we will tell the computers what is the X variables for the prediction period. Okay. So here, since we are doing a 12-month prediction, so we need to tell computer what is the value of the X from October 1987 to September 1988. Okay. So we will use this called like new XREC. Okay. So there's something new. And this is equal to an new rec. Okay, and this new rec is like the values of the X in the prediction period. Okay, and then let me run this code and let's see the prediction. Okay, so that's a prediction. It's again like this red is a prediction and this shaded region are the confidence intervals. Okay, so you can see, okay, the predictions looks pretty reasonable. Like right when you look when you compare it with the previous data, it looks pretty reasonable, I think. Okay. Okay, so any questions about the prediction? Or especially like the code of the prediction? Yeah, so you need to specify the X values are in the prediction period. Okay, and for the time, you can use this code to specify it. Okay. Okay, and I want to talk a little bit more about like this forecasting based on your project. Okay, so I know that some of you are doing like the effect of COVID on economic variables Y. Okay, and let's say that you want to predict Y, those like economic variables from May 2021 to April 2022. Okay, so in this case, your new reg here should be the COVID-19 cases from May 2021 to April 2022. Okay. The problem is that actually we do not observe it. Okay. So in order to the predictions, you need to do something more. It is not observed from our data. Okay. So there are a couple of options. So I have in my mind. So the first option that I have in my mind is that you might argue that starting from May 2021, the COVID-19 case would be less than 1,000 each day, okay, daily. So which I believe if like the COVID-19 cases drop to below 1,000, then there would be zero effect on the economic variable Y. Okay, so for example, you want to study like the effect, I know, some study effect of like the X variable, the COVID-19 on gasoline price, then I would say, okay, if the COVID-19 cases drop to less than 1,000, then I believe it won't have any effect on the gasoline price. Okay, so if you have this, maybe you can cite some other papers or you can cite some like previous studies, not COVID, maybe some other disease, something like that. So then you can say that, okay, so if I believe this is the case, then I can just use COVID-19 equal to 0 for my prediction. Okay, so you can just set like COVID equal to 0 from May 2021 to April 2022. Okay, yeah, but I think that might be a little bit like crude. Okay, I think a more sophisticated way is that you first try to fit a SRAMA model to COVID-19. Okay, so you first consider like COVID-19 as a time series and you fit a SRAMA model to that. Okay, so no X regressors include, just the COVID-19. Okay, okay, then you use your model to predict COVID-19 from May 2021 to April 2022. Okay. Then you will use that predicted COVID-19 for your Y value prediction. Okay. Yeah, so for example, if you predict like the May 2021 COVID-19 from your SRAMA model, if you predict the COVID-19 cases in May 2021 is say like 10,000, okay? Then you will use 10,000 as the COVID-19 cases for your gasoline price prediction. Okay, yeah, so you first predict the COVID-19 case from an SRAMA model, then you use that predicted value for your final like prediction model. Okay, so I think this way might be a little bit better than the first option. Okay. Okay, so any questions here? Okay, so if there are no questions, I think that's the fit a SRAMA model of Y with regressor X. That's all the things that I want to talk for this topic. Okay, so just go over it again. So you need to follow like all these 6 steps to do the analysis, and the analysis might not be that easy. So you might spend some time. Yeah, and the hard part perhaps is forecasting. Okay, so if you do not have the data for X variables for forecasting, you need to make some adjustments for that. Okay, so that's it. So starting from today's class, I think we are pretty much done with the SMM. So we will move to a new topic. Okay, the Gauch model. So let me switch to the whiteboard to start with some theories of the Gauch model. Okay. The Gauch model reading is SS 8.1, and we have a R code for today. So let's first talk some theories about this Gauch model. And this is actually a very, very important model in time series analysis. So let's start with the ARMA model and talk about some limitations of the ARMA model. Okay, so the ARMA model. So the ARMA model basically models the conditional mean variance is not constant. So for example, let's consider this AR1 model. Okay. So the conditional mean of this AR1 model is equal to phi0 plus phi1 xt minus 1. Okay. So more importantly, this AR1 model, or also like all the ARMA model, is that the variance or the conditional variance of this model is a constant. So you can show this is just equal to the variance of the white noise part, WT, and this is sigma W squared. Okay. So that's the important parts of the ARMA model. So the conditional variance of this ARMA model is constant. Okay. So this would help us to estimate this model, but it actually has a lot of limitations. So as we've seen in a couple of like our previous examples, we find like the conditional variance is actually not always a constant. Okay, so limitations. It's not constant. Okay. So how do we like address this non-constant variance problem? So like in our early class or previous class, we discussed we will take the transformations. We usually take like the log transformation, but sometimes you can also take like the square root transformation, or even more generally like the box cost transformation. Okay, so that's one way to address this. And another way to address this is to use this arch model. Okay, solution. So this G stands for the generalized autocorrelated or autoregressive conditional heteroscedasticity. Yeah, so that's the full name of this model. It is called the generalized autoregressive conditionally heteroscedasticity model. Okay. The model that people start with is usually the arch model. So it's the autoregressive conditionally heteroscedasticity model. Yeah, and this is a very important model in time series and especially in finance. So I can actually like this arch model, this autoregressive conditionally heteroscedasticity model is a model that wins the 2003 Nobel Prize. So it's a model like introduced by, I think, Robert Engel, and that model helped him to win the Nobel Prize. And after that, I think his student, I think Tim Belosov, I think that's the person, he's in Duke. He generalized this arch model to this so-called like the generalized autoregressive conditionally heteroscedasticity model. And like this arch model even has like a very good shot to win the Nobel Prize, even though he hasn't won yet, but he still has a very good shot to win that. So you can tell that this arch model and this arch model like really is very important. Okay, so I think it's but they are actually very complicated compared to the AMA model. But I still think like it is good to introduce this model in this class. Okay, so we will talk about like the basics of this Gauch model. Okay, so now let's start with the arch model. Okay. So in finance, so this model is like usually in finance, I mean, finance is a very good application of this model. So we are concerned with like the return or the growth of some assets. Okay, so in finance, we are concerned modeling the return, the growth rate of an asset. Okay, and we usually use this to model it. Xt minus xt minus 1 over xt. Okay, and this is just approximately equal to the difference of log xt. Okay, so that's why we use like the log transformation. Okay, so we are usually interested in the return of an asset, and that's equal to the current value minus the previous value divided by the current value. Okay. And we usually find that return, let me write this, return has this following properties. We usually find that the mean of the return is equal to 0. Yeah, so that's really shock, right? So if you like invest in assets, and actually you will find that the mean of the return is actually 0. So why do you want to do the investment? Okay, but that's what people usually find. The mean of like the return of an asset is usually 0. Okay. Second, conditional variance is not constant. And number 3 is highly volatile periods tend to be clustered together. Yeah, volatile, I think, is a very finance word. It just means like the variability. So that's people usually find in finance data, like in the stock market data. So that's people usually find. Yeah, and I know like some of you are also doing like the stock data study analysis for the final project. So that's maybe one extension you can consider. Okay, so that's the thing that people usually find. So the question is that how can we model this? Okay, how can we model these 3 properties? So like the bottom line is that it looks like this AR the ARMA model perhaps is not a very good choice. The reason is that the conditional variance in the ARMA model is a constant. It does not depend on time. But actually what we're seeing like in the finance data is like the conditional variance is actually not a constant. It's actually depend on time. Okay. So I think I want to switch to the R code to first give you an example of this, okay, to tell you like actually like what these 3 properties actually mean in data. Okay, so let me switch to the R. Okay, so this is an example. It's the Dow Jones return data. Okay, so let me first plot the data. Okay, so this is a Dow Jones return from 2006 April 21st to 2016 April 20. Okay, so let's say like what each of the properties we discussed have in this figure. So first you can see that the mean is pretty much 0, right? And we can actually find its mean by just using this command. So you can see that the mean is just approximately equal to 0, right? And the second thing that you will notice is that the variance is not constant, right? So for example, in the this is I think the financial crisis. During the financial crisis period, the variance is much larger than the period that does not have a financial crisis. Okay, that's property number 2. So the variance is not constant. And property number 3 is that the periods that have high volatile are usually clustered together. And this is very easy to see, right? So you can see that, for example, during this financial crisis period, the volatile or the variability of the data tends to be very large. Okay, and after that period, the variability tends to be small. Okay, and the larger variabilities tends to cluster together. So for example, the financial crisis is a period that you can easily see. And also I find like in year 2012, you can also find some clustered high volatile periods. And similarly like in 2015. Okay. Yeah, so that's the Dow Jones return. And I think if you check like the return of other assets, you will pretty much see the similar patterns. The mean is 0, the constant, the variance is not constant, and the high volatile periods tends to be clustered together. Okay. All right. So let's also run this ACF2 plot. Okay, the PACF and the ACF of this Dow Jones return and see what we can see. Okay, so what you can see here is that the ACF and the PACF, it looks like a ARM11 model can fit this. So it looks pretty much like a white noise, right? We do not see any seasonality pattern here. Very easy to see. And I realized that almost like all the lags are within the confidence intervals. Okay, so this looks pretty much like a white noise. Okay, and this actually does not contradict with our findings. Okay, so we find like the mean is 0, the variance is not constant, the high volatile periods tends to be clustered together. And this graph also tells us, like in this very specific example, the Dow Jones return looks pretty much like a white noise, or maybe at least an ARMA11 model can fit this. Okay, but as I said, like the ARMA11 model, it looks like it fits the ACF and the PACF plot, but it certainly does not like fits this heteroscedasticity pattern. Okay, so we need a new model to capture all these properties. Okay, so that's the ARCH model that I'm going to introduce today. Okay, so now let me switch back to the whiteboard and introduce you the GARCH model. So we'll start with the very simple ARCH1 model. Okay, let's talk about the intuition first. Okay, so that's our return. And if our return is just equal to sigma t, where sigma t is a white noise, it certainly does not fit our like Dow Jones return, right? Because the variance is gonna be constant, but certainly that's the variance from the Dow Jones return is not constant. So this is certainly not correct. Okay, so how can we fix this? Okay. Let me see. So let me write in this way. So intuition. So if our RT is just equal to epsilon t is a white noise, then the variance of RT, which is equal to the variance of epsilon t, is sigma sigma epsilon squared. Okay, so this is constant. This is not the thing we want. Okay, the question is how to improve it. Okay. Right. The idea is actually very simple. So we add some like variance in front of this white noise. Okay, so solution. Let's add another term called sigma t in front of this epsilon t. Okay. So if this is the case, then what is the variance? So now the variance, or let's say the conditional variance, which is the thing that we are looking at. Okay. So now is equal to variance of sigma t epsilon t, sigma t minus 1, epsilon t minus 1, sigma t minus 2, epsilon t minus 2. Okay. So let's think if this sigma t has some dynamics. Okay, so that is sigma t is related with sigma t minus 1 or sigma t is related with RT minus 1. Okay, so if sigma t, these are just some examples. So if this sigma t has some dynamics, then you can easily say that the variance or the conditional variance is not a constant, right? Because this sigma t is related with sigma t minus 1, or highly likely the sigma t is also related with this sigma t minus 2. So intuitively speaking, this conditional variance is not a constant. Okay. So this would suggest that the property 2, or which is the non-constant variance, is good. Okay. So if we have this sigma t, and if we allow this sigma t to have some dynamics, then our model can capture this non-constant variance property of the asset returns. Okay. So which is good, right? Okay. And more importantly, if the sigma t has dynamics, then RT would be related to RT minus 1. Why? Because RT is sigma t epsilon t, right? And RT minus 1 is sigma t minus 1 epsilon t minus 1. And we assume there's some correlation between sigma t and sigma t minus 1. Okay. So this would satisfy our property 3. That is a high volatile period tends to be clustered together. Yeah, so if your sigma t has some dynamics, okay, then your current period return would be highly related to your previous period return, or possibly your return 2 periods ago, early. Okay, so that would like make your graph like the high volatile periods tends to be clustered together. Okay, and also like the low volatile periods also tends to be clustered together. Okay, so you can easily see that if we introduce the sigma t in front of the epsilon t, and if we allow our sigma t to have some dynamics, then it seems that we can capture the properties of the figure, okay, of the asset return figures. So to make it more formal, I think now it's a good time to introduce the Arch-1 model. So the Arch-1 model is this. So RT is equal to sigma t epsilon t, and we will introduce some dynamics in this sigma t. Okay, so the dynamics that people introduce here is sigma t squared, okay, alpha 0 plus alpha 1 RT minus 1 squared, okay, where alpha 1, alpha 0 are both larger than 1, and the sigma t just follows a standard normal distribution. Okay, So that's how we formulated this Arch1 model. So it satisfies this RT equal to epsilon t, sigma t epsilon t like formula. And the dynamics that we introduce for this sigma t is it is related to RT, and it is related in the quadratic form. Okay. All right. So now let's work on some properties of this Arch1 model. Okay. Number one, we can show that the expectation of RT is equal to 0. Okay. Yeah, this is actually not very easy to show. So it would spend some time, but the result is that it would equal to 0. The mean is equal to 0. Okay. The second is that the variance of this RT is equal to this alpha 0 over 1 minus alpha 1. Okay, but that's an important thing. The conditional variance RT given RT minus 1 is equal to alpha 0 plus alpha 1 RT minus 1 squared. So do you notice the difference? So this part, this variance does not depend on time, does not depend on time. But this part do depend on time, does depend on time. Right, so this is actually exactly what we're seeing from our Dow Jones return, right? So we're seeing the mean of the return is 0. And we're seeing like the ACF and the PACF plot suggests that it looks like a white noise. So we will say that its variance is not, it is a constant. And this is what we see here. It does not depend on time. However, we see like the variability of the model is certainly not a constant. So we find like the conditional variance of the return is not a constant. It actually depends on time. Okay, so you can see that this Arch1 model captures all the features that we see in our Dow Jones return data. Okay, yeah, and of course you can also see that this Arch1 model can capture the property that the high volatile periods tend to be clustered together. Okay, and intuition is that this sigma t has some dynamics, which would make like the RT, the current period return, and the previous period return highly related. So that's why we will see the high volatile period tend to be clustered together. Okay. That's the first two properties of the Arch1 model. The third property is that this Arch1 model can actually be written as a, or I mean, is equivalent to a non-Gaussian AR1 model. Okay. So why this is the case? So let's write RT squared sigma t squared. Okay, so I just like take the power 2 on both sides of the Arch1 model. Okay. And let's write it this way. Okay, so this is the Arch1 model. Okay, and then let's take the difference. I think I'm wrong, sorry. sense. Okay. Let's just collect terms, and what we got is this. Okay, so this is a non-Gaussian AR1 model. Okay. Why this is AR1 model? So the RT square is on this side, and the RT minus 1 square is on the right-hand side. Okay. So if you think like RT squared, let's call it XT, then this is exactly XT equal to alpha 0 plus alpha 1 XT minus 1. Okay, and this is your error part, but unfortunately, this is not a white noise error part. This is a non-Gaussian error part. Okay, this is a non-normal white noise. Yeah, but certainly it's like follows like this AR1 setup. Okay. Yeah, so which means that the properties that we have for the AR1, for example, like what coefficients, like the range of the coefficient we want to have alpha 1 also applies here. Okay. So that's the 3 properties I think I want to cover for this Arch1 model. The first 2 are important because it just shows you that why this Arch1 model can capture the Dow Jones returns, the asset returns figure. So why it can capture that in a formal way. Okay. All right. And estimation. So estimation, I won't spend time here. So the estimation, we will just use the maximum likelihood estimator. Similar to the SRIMA model we discussed, we'll just use the property that the epsilon t follow, or the epsilon t follows a normal distribution. Okay. Yeah. So we will just let the computer to do the estimation for us. Okay. So what we just discussed is AR1, and actually we can generalize this to AR. What we discussed is the Arch1, and we can actually generalize this to an Arch-P. Okay. So for the Arch-P model, the RT setup is the same. So RT is still equal to sigma t epsilon t, and this epsilon t is a noise. Okay. So the difference is the dynamics of the sigma t part. Okay. So instead of assuming it's like it follows somewhat like an AR1 process, we assume like the sigma t squared now follows a ARP process. So here you can see the dynamics of this sigma t becomes richer than the Arch1 model, right? The sigma t not only depends on RT minus 1, but the RT minus P also affects sigma t. Okay. Yeah, but the key is that this is the same. Okay, this is very important. So we do not do like transformations or like introduce more legs in this main equation. All we do is to introduce some legs for the dynamics of this sigma t. Okay. Yeah, and of course, you can imagine that this Arch-P model has conditional mean equal to 0. The conditional variance is not constant. And moreover, it can capture the feature that the high volatile periods tends to be clustered together. Okay. Okay. We can actually, we can actually make this model. We can introduce more features in this model actually. So this is a ArchP, right? We can actually make it a ARMA ArchP model. So how to do that? So first note that this RT has mean 0. Okay, as I said, this is actually not very easy to show, but it can be shown like this. RT has mean 0, and why people do that? The reason is that it comes from like the asset pricing, and in the asset pricing, the mean of the mean of the return is 0. So that's people usually assume that the RT has mean 0. But we can of course that do allow it to have like a non-zero mean. Okay, so we can certainly relax this. And that's the expectation of RT not equal to 0. And to this, let me introduce this ARMA arch model. So this is mu t plus sigma t epsilon t, and sigma t squared equal to okay. So if this mu t is equal to, let's say, phi 0 plus phi 1 RT minus 1, then this becomes a AR1 arch P model. Okay, so why this is, to write it more clearly, this is RT is equal to phi 0 plus phi 1 RT minus 1 plus sigma t epsilon t sigma t squared alpha 0 plus alpha 1 RT. Okay, so this is AR1 arch P model. Okay, so you can see the AR1 part is this, and the arch P part is this. Okay. Right, so the difference between this, like this ARMA arch model with the ARMA model is that we introduce this. This is a key part. We introduce this sigma t in the like in front of the epsilon t, and we allow the sigma t to have some dynamics. Okay, and the reason that we want this to have dynamic is that because we want to capture the high volatile periods tends to be classed together, and we want to capture the conditional variance is not constant. So that's the two things we want to capture, and we introduce this epsilon t. Okay. Yeah, and definitely you can imagine if mu t has, write this. Yeah. So if we allow mu t to have more ARMA, to have more AR or MA lags, then this becomes a ARMA PQ arch P mode. Okay. So any questions about like the setup of this model or why we want to consider this model? Okay, so I think it's time. Yeah, I think it's time. So next class, we will discuss how we can fit this ARMA arch model in R. And then we will generalize this ARMA arch model to the ARMA Gauch model. And we will also discuss how we can like implement the ARMA arch Gauch model in R. Okay, so let me know if you have questions, or and that is for today's class. Okay. Thank you.
Thank you.